Okay, so we have just started recording, and we will now start the session of today. All right, so good morning, everybody, ladies and gentlemen. Thank you very much for joining us in a new session of the solar photovoltaic course for the ERC program. In today's session, we are going to talk about large photovoltaic plants. Okay, sometimes we call them solar parks or solar farms or PV farms. Okay, as an analogy to the wind farms, etc. Okay, we have today's program. We're going to see, if you remember, in the previous sessions, we have been discussing about technical feasibility studies. This is what we are exploring these days. And for the rest of the course, until we finish in February, we are going to be discussing about technical feasibility analysis and techniques, etc. So today, we will be sharing with you some concepts and some techniques, experiences about PV farms. We are going to follow the same structure as the previous sessions. Okay, if you remember, we have this list, generic list, 8 items. All right, where we started with a planning framework that I discussed with you last week, and the integrated approach, different elements. Remember, social part, the organizational or institutional component, also the technological component, and the economic and financial component. So we discussed that last week. Today we are going to take a look at the specificities of the large PV systems or PV farms. Okay, so we will be discussing some issues about the site assessment. Then for the energy demand, obviously, in this case, we are going to be talking about systems that are injecting, they are generating power plants, all right, and injecting all the production to the grid. So we don't really need to, there is no case for energy demand because it is the grid, yeah? We can talk about the capacity of the grid, yeah, to accept or not all the production, we call it, yeah, dispatchability. Okay, but not really the demand, the final user demand that we were discussing for the off-grid systems. So this is not applicable for PV farms. Then solar radiation, different configurations, and precising modeling. We have seen these things for PV systems. And today we'll be mostly concentrating, apart from size assessment, in the definition of outputs and inputs, yeah, for the specifics of PV farms. Then the equipment, also civil works, all right, and component requirements for PV farms, and the operation maintenance and the human resources that are needed, again, for PV farms, okay? Today, together with me, I have a colleague from my office. His name is Jean Antonio. He is a very experienced engineer, okay? We work together in solar projects, so he has a lot of experience with PV farms, so he will be giving the session with me, okay? Joan, if you want to say hello.
Hello, good morning. I hope today we have a good session. I think it's an interesting session.
Yes, thank you very much, Joan. So Joan is in my office, in my team, and we work together with some projects. Yeah. So Joan will be explaining some details on the PV farms today. Okay. So let's move on. All right. So the first issue we need to think about when we consider a PV farm, obviously, is the site, yeah, the place, the location where we are going to consider a possibility to install a PV farm. Okay, issues like the accessibility, the roads, communications are very much important. We need to be able to access the area. Also, how is the grid, the transport and distribution grid arriving to that particular site? What are the capacities of the grid in around that area? What is the distance to the last substation existing at the moment? What are going to be the land affectations, right? Are we going to be using probably somebody's land or considering to use somebody's land, right? So this ownership, if we have to think of eventual, expropriations, the conditions for that, legal issues, economic compensations, etc. So these are, of course, items that we need to consider when we approach a site assessment for a PV farm. Then, as I said, the dispatchability of the grid, the existing line and its capacity to evacuate all this power we could be generating in the site, but also what would be the impact, all right, in the quality of the grid. We have to observe the grid codes, okay, what are the regulations, and that could mean that we will have some limitations, okay, in terms of what kind of plant, power plant we can build, solar plant, or what are the capacity or the plant factor, okay, limitations that the grid quality, the grid code might impose on our PV plant. So perhaps there could be the possibility where all of our potential production in the PV plant will not be able to be sent or injected to the grid due to some limitations, and that can have economic or financial implications in our projects, obviously. Okay, so let's continue with our example. This is just an example, we just chose this area as an example because we have been looking at our case in Uruguay, not because we are thinking or proposing a specific PV farm in Uruguay. This is just an example, a case, okay? So we already have some lines here, 100. The image, sorry, is not perfect, but we have already a line there, 110 kilovolts, I think, or 15. So, okay, Uruguay could be an area where we could be, studying the possibility to have a PV farm. Okay, why not? So once we have a look, or we have analyzed the site and its key implications, obviously these things we are mentioning, they require a proper study, a detailed analysis, etc. And here we are just presenting, okay, the case. Obviously, this kind of projects they can be very expensive. They can mean a very high investment, like the one that you have done, EDM has promoted in Cuba. So they are not small systems and obviously need to be addressed carefully and in detail. So the next step would be to go and understand the feasibility of the inputs and the outputs of the PV farm. And basically, we want to highlight two aspects here: the verification of the solar radiation levels. Remember last week we discussed about the advantages, limitations of using databases for solar radiation, and sometimes the convenience to have the own data, specific measurement, okay, of radiation levels in the site with the pyranometers or specific equipment, to get very precise and accurate data on the site. And then another aspect would be to analyze and compare what could be the generation options with a fixed PV field or with some tracking options. We presented also a couple of weeks ago. Remember about the solar resource, we have seen these maps many times, okay, in this course, because it is the solar radiation and the photovoltaic production potential. Very important all the time. We start all the projects by looking at the radiation. And in this example we are following, obviously, we will be looking at what could be, in this case, we can use the map on the right, because if you remember, the map on the right is already considering a high performance ratio that we said is only applicable, or only in our recommendation, yeah, really accurate to be used in grid connected applications. Okay, so we take a look at where Gurue area would be, and according to the color code, or this map can be checked out in detail. This is the Global Solar Atlas. We get that the yield, the yearly production that we can expect, okay, with a PV system, Gurue, would be around 1,600 kilowatt hour for every kilowatt peak that we install. Okay, this is the color code, all right, approximately in this area, in this range. So 1,600 kilowatt hour of electricity generated every year per each kilowatt peak that we install. So now it's time for you to start, doing a bit of calculations, a bit of exercises. By looking at the area around Gurue, we can see, this is just an example, okay? Well, what looks like being some interesting, okay, area here that could, why not, host a PV farm, all right, a large PV system in this area. We have more or less a triangle, approximately a triangle. We have measured it, so it's more or less around 24 hectares, okay? 24 hectares of land. And now I would like to hear your opinions. Huh? Don't be shy. We are colleagues here. What would be your proposal? What kind of system do you think we can put here? What would be the size? Do you have any idea? Anybody? Anybody has an idea how many kilowatt peak we could put here? What would be the production expected in this triangle? 24 hectares in Gurue. Anybody, please? "24 hectares of land is quite a substantial, yeah, part of land. So can we put here 1 megawatt peak, half a megawatt peak, or even more? Anybody have an idea? Okay, I understand. Yes?
I think maybe 20.
20 what?
Megawatt.
20 megawatt? Okay, thank you. We have an idea.
Interesting.
Anybody else? 20 kilowatt peak? 20 megawatts?
Megawatt.
Yes, 20 megawatt. Yes, anybody?
Yeah, I think also it's approximately 24 megawatt peak. It's true that will depend on the efficiency.
Yes, thank you. It will depend. Thank you. 20
of
Oops.
24.
Yes, sorry, we cannot hear you very well. Signor Inocencio Guglielmo, I'm sorry, we cannot hear you very well.
Yes.
I think you said it depends on the efficiency, right? 20 or 24 megawatt,
Yes.
but it will depend on the
Yes.
efficiency, yeah?
Yes. Yeah.
Thank you. Yes, you're very right, yeah? One first question we should consider is what kind of structure, what kind of configuration we're going to use. Is it a fixed structure, or are we going to consider trackers? Let's keep your reference 20, 24 megawatt peak. Yeah, thank you very much. So let's remember, yeah, with the tracking systems, we can get a little bit about 15% of more electricity production with one axis tracking, whether it is horizontal axis or vertical axis. Yeah, horizontal axis will help us to track the sun altitude, that is the modification of the slope, inclination of the panels, and the vertical axis will help us to track, yeah, the solar path with the azimuth, yeah, the orientation from the east to the west. All right. Again, more or less, you can consider 15% extra generation. If we have both axes, obviously we can increase the production about 30% compared to a fixed system. Yeah, we have already seen pictures, etc. We will see some more later on in this session. Okay. Now that we are talking about trackers, Joan Tony, I think you wanted to mention some. We'll go back to the exercise in a minute. Yeah, don't worry, I haven't forgotten about the exercise. But let's have a look at some comments here. This is some projects that we have done, and Joan and Tony wanted to tell us some experiences here, please.
Yes. Okay, Ben. This is the picture is of a project of Alstom Renewable in Spain around year 2005. It was 140 dual axis units for a total power of about 1 megawatt. It's a little power plant, but in this year is a big plant in this moment. A detail of the PV panels is the power, because this is a panel of 175 watts peak each panel.
Each panel is 575, yeah?
Yes, the fabricant was Solon, is a German company. They were the largest PV panels ever made. Includes arrived to a level power of 775 watts peak each panel. Unfortunately, this company closes between the years 2013, 14, and had to be converted for the small panels. Currently, there are no panels of that size yet. But the important is the project. There's a project of a dual axis, or the other is the next slide, please. Thank you. This is another project in a dual axis. This is the prototype. This is not the power plant. Is the prototype scale 1.1. And then this is a dual axis of 25 kilowatts peak by tracking. It was installed in the south of the Spain, 200 dual axis to building a power plant of 5 megawatts. This is the largest dual axis tracker that I have ever seen. The manufacturer is a company in Spanish. The name is Ades. Is still operating, but actually it's offering other trackers that are less heavy of this and can fit into the price of the current market, because you seen before that the dual axis is a problem to install with the price of the panels currently.
Okay. Thank you very much. We can see here, yeah, some examples of trackers. So we go to our exercise, okay? Okay, you have mentioned a reference of 20 to 24 megawatt, okay, peak of power. That is very much accurate, yes, if we consider a fixed system, okay, more or less. That's probably the reference the gentleman that answered have in mind, about roughly 1 megawatt per hectare, okay? That is very much, yeah, a good reference if we use fixed system. But if we use tracking, the trackers, because they move, they require more spacing in between trackers, okay? So that they don't cast any shade to each other. So if we use dual axis, like the example we have shared with you here, we will need to space them much more. So for each megawatt, we will need 5 times more space. If we only use one axis, single axis tracking, it's double the ratio than fixed, a fixed system, all right? So if we consider fixed system, yes, 24 megawatt, I agree, okay? We agree with this reference. If we use a tracking system, it would be less. In our example area of 24 hectares, you would be able to install less than 20 or 24 megawatt, okay? Now, apart from the quantity of panels, okay, of PV installed capacity, what would be the cost? Obviously, that is the second big element we need to consider, yes, in a feasibility analysis, even if it's a quick estimation, yeah, like the one we are doing, just using satellite image and having a first reference of cost. So even though the prices are coming down, yeah, still, you know, the references are more or less like this we're sharing here, roughly about $1 per watt peak, okay, below $1.80 per watt peak in a fixed structure system, all right, up to $1 per watt peak, single axis tracking, and double than that for dual axis tracking, okay? So let's continue with the exercise. What would be the expected production of electricity that we could have in our triangle, 24 hectares? Of course, the expected production will change if we use fixed structure or if we use trackers. Who can give us a reference? What would be, how many megawatt hour per year could we generate in this 24 hectare triangle area in Goodway? Who has an idea, more or less? Anybody in the room? By now you should be able to do this calculation with the references we have given. For instance, if we use a fixed structure, we can put, we set more or less, yeah, 1 megawatt per hectare, so that's 24 megawatts installed.
And excuse me, what would be the location to
In
know
here?
the solar radiation?
I showed
Yes.
that before.
Yeah.
Good idea. Good question. That is it. Good. Okay. 1,600 kilowatt hour per kilowatt peak per year. So how many megawatt hour you have to multiply? Yeah. All right. Can anybody give me a reference? More or less. If we put 24 megawatt peak times 1,600, how much we get?
It's 32,000.
32,000, or a little bit more, huh? If you multiply, if you use 20, yes. If you use 24, it's a little bit more. If you use 24, you will get 38.4 gigawatt hour per year, or 38,400 megawatt hour per year. Yes. If we use trackers, we will be able to install less PV panels. Remember, we have to space them. So the system could probably be cheaper. We will see now the cost. Yeah? But then the generation is proportionally higher because of the tracking. Okay? So you see, in one same area, we could be expecting different yields, right? Different generation levels, depending on the kind of tracking or fixed structure that we use. Now, what about the cost? Who can give me a price estimation, investment cost estimation? What do you think would be the most interesting solution for this triangle here in Gurue? We go for fixed structure always because it will give the most PV capacity installable. We always go for fixed, or perhaps there's some possibilities with the trackers. What do you think about the cost? Let me show you. Yeah, you have the handout anyway. We sent it yesterday, but these are the cost references. 0.8, $1, $2. Okay. Who can give me an idea how much this PV farm could cost in Gurue? Anybody? Okay, no options, no references.
I'm not sure. Maybe 38 million.
Maybe, sorry, 38 million?
Sorry, 30 million.
30 million?
But I'm not sure.
Of course, no problem. 30
Can you
million,
go to the
30 million, $30 million, 30. Anybody else? Remember that
yes?
you can, yes, please come in. Yeah.
I think that I don't know if I'm correct, but I think that is simple. If we know in each type of we're talking of fixed, single axis, or dual axis, we have a price of each megawatts according to the type of this one. We just multiply. For example, we have $0.8 per megawatt. If we are talking about dual axis, we just multiply this number per 0.8 and we'll find the investment that we know we need to cover this system.
Exactly.
We do the same with single axis and the fixes.
And what number would you get, more or less? Our colleague said 30 million, 30 millones de dólares. What number do you get? What do you think?
1 minute, so sorry.
More or less.
38,400 plus. Yes, let's suppose that this first one fixed is for 0.8 dollars per megawatt. I don't know because I can't resist the number of the previous slides. If is it possible, you can go to the previous slide. Yes, yeah, it's good. It means that the first you can beg. Another one.
Fix it.
Yes, fixed $0.8 per water peak. It means that we considered 24, 38, was about $30,720.
So you do 24 times 0.8.
Yes.
And this is 19, right?
The reference, the reference dollar by watt peak is the same that millions of dollars of millions of watt peak. It's probably more easy for it is the same millions megawatt or use dollar watt peak is the same relation.
Exactly. So we multiply this by 0.8 because these cost references, they refer to the peak power capacity, okay? The power of the plant, not the generation, not the energy, the power.
The power, yes.
Okay.
However,
so if
you are using the dual axis,
yes,
the cost might drop to 20 million, about 20 million.
Because it's 4.8 only. If you get dual axis, then you have to multiply this times $2 million per megawatt peak. Okay. So if we calculate this with the references we gave you, thank you very much, Mr. Cesar, and Mr. Frade, thank you very much for your contribution. So if we multiply this, sorry, I changed. We have this situation where the investment, okay, needed to install the fixed system, because we need to put much more peak power capacity. Remember, it's 24 versus 12 or 8. The fixed system will be more expensive, obviously, okay? We need to spend roughly $19 million. If we go for single axis, $12 million. If we go for dual axis, approximately $10 million. But the production we will receive, we will get out of that is of course different, okay? If we install more PV panels, we will get more production, but the efficiency, the yield, the productivity is higher for the tracker, to the extent that if we compare what is the equivalent cost, investment cost, for each unit of electricity we can generate per year, we see that the fixed solution and the one axis, single axis solution are quite similar in the end. The investment cost per energy generated unit is quite similar. So from the point of view of the investment, if you are thinking from EDM point of view, why not? Or ministry, or even as a private developer, both options are more or less equally efficient in terms of the techno-economic performance. While one option is cheaper and the other one would be more expensive, the cheaper option will produce less electricity. The more expensive option will produce more electricity, okay? But the efficiency of the investment, let's say, productivity is quite similar, okay? Oops, hello, somebody has turned the screen on.
There are some problems. I don't know what is the problem.
Wait, no. Stop touching things. Who is that? Somebody has been sharing. Okay, no problem. That's fine. Hold on, just give me a second. I'll fix this now. Just a second. Okay, everything is fine, yeah, again? All right. Good. Let me check. That's fine. I think we are fine again, yeah? Okay, good. Okay, so I think that's the purpose of the exercise we had, yeah? So just to show the different options. So that is a relatively yeah, quick and easy.
I'm sorry, Paul. I want to comment a little question only. It's
yes.
not a problem. Then this is the parameter of the right is a simple criterion to analyze the investment about the energy generation, based only in the capex, not in the opex. It's need to analyze in the future. But another is you can see the solutions with fixed structure or with single axis are more or less the same, but this not in the time the same. The dual axis seems not to have to be considered, but this situation is in fact the same in all the PV farm projects in the world. No, actually, but not in the past. When the best solutions were in the past, the best solution were dual axis. Is when the panels price around the price of the $3 by watt peak. Now the price is more or less $0.5 watt peak. It's the ones that this means that you need other parameters to evaluate the best solution. The OPEX, obviously, but the power capacity of the grid, of the need of the minimum or maximum energy production, or the budget limitation, etc. Sorry, Paul, this is only a little acceleration.
That's fine. No, thank you. Yes, as John was telling us, this is very, very preliminary assessment. But these two aspects, the cost and the PV capacity, you can fit in a site assessment, is something you can do very quickly, even before going to the site, and so that when you go there, you already have like a preliminary approach on what the possibilities could be, and then you can build a portfolio of areas, all right, based with this very simple characterization. Obviously, there are other aspects we need to check. Many more inputs and outputs that we will be now exploring in a bit more of detail. But we wanted to share this quick exercise with you so that you have a first idea, on the very quick precising for large PV plants. All right. So other things we need to consider: the power capacity of the inverters, of course. This is a technological area that is evolving rapidly in the market. Okay. The inverter industry offers us many models, and the capacities are rising. At the moment, we even find inverters with a rated capacity of 5 megawatt converter power capacity, okay, and even increasing. For instance, a Chinese manufacturer called SunGrow is currently offering containers of inverters that are almost 7 megawatt each container. All right, okay. So for our example, we're doing for Goodway. Imagine if we are using this option, of single axis, okay, solution 12, this is the cost, 12 megawatt peak, okay, with only 2 inverter containers of SunGrow, we could have enough for the whole plant, okay? So very big inverters. Other issues we need to check are the voltage levels, both in direct current, okay? Typically, rated voltage currents on the DC side were below 800 volts. But again, nowadays, inverters allow the input receiving DC input voltage levels above 1000, 1200 volts, or even 1500 volts, all right? Obviously, these are very high voltage levels that will require detailed, all right, design of the DC lines. Working at these voltage levels is convenient because we can reduce cost, we can reduce losses, okay, even for relatively longer distances for our DC conductors between the PV panels and the inverters, okay? And in any case, the national codes and electricity regulations always must be observed. Another aspect that we need to check are the voltage levels in AC, okay? Inside the PV park, inside the PV park, we will have an internal grid between the inverter, which could also have the transformer together with the inverter. We will see this in a minute. And this would be the connection between the inverter or inverter and transformer and the substation. Substation would be, let's say, the gate, yeah, the exit of our plant, and the connection to the distribution or the transport grid. And this is a decision of the design, a design decision for the PV project. How to do this line could be 15, 33 kilovolts. In any case, another AC grid, but this case a low voltage one, a line will be needed to feed the auxiliary equipment we have in the PV farm. Okay, the monitoring equipment, etc. The trackers. Okay. And finally, another voltage level AC we need to design and to define would be the interconnection levels, okay? And that will depend on the grid operator in each country, in this case for EDM, yeah? Could be a requirement to interconnect the PV farm at 33 kilovolt line. In Spain, sometimes some PV farms have been connected at lower voltage levels than that, even down to 25 kilovolt. But if the PV capacity, the PV park capacity is big, is large, it might require the evacuation, the connection to be designed and branched at higher voltage levels, 110 kilovolt or even 220, okay? Now let's start looking a little bit at the different stages or subsystems in the PV farm, okay? Let's look at the drawing here. We took this example from the company, yeah, that built Mukuba plant, okay? So Scatec Solar, and very much this schema refers to refers to the kind of system that we have in Mokuba. So it's more or less 30 or between 30 and 50 megawatt PV farm, okay? Sometimes they are also called utility scale, okay? PV systems, where we have the solar modules with trackers, then the inverters, depending on the size of the inverters, you have more inverters, less inverters. This example, if you see the reference for 800 trackers, 20 inverters. Obviously, these are large scale inverters. Then transformers. And finally, the substation that will make the interconnection of the PV farm to the power grid. Okay, so essentially these are the main elements in the PV farm. Then on top of that, we have the control, monitoring, and communications and control systems. Okay, so for the rest of the presentation now, we are going to be discussing or presenting these elements to you one by one. Okay, and don't worry if we don't have enough time today, we can also continue. Yeah. Any other session, so don't worry. If the time is a little bit short today, we will revisit these concepts in the following sessions. Okay, so now that we have seen more or less what are the inputs and outputs, generally speaking, the key aspects, let's look at the requirements. Okay, the specific requirements that we will have, all right, to deliver these outputs and to deal with these inputs that we described. We have these 5 key areas of concern: the structural, okay, the structures, or the trackers or no trackers, fixed, etc. The risk of flooding. Okay, this is very important. Anticipation of potential problems with floods, heavy rains, meteorological condition, etc. And the mitigation aspects, the drainage, okay, planning. This is, of course, very much civil works requirement, all right? Then issues related to the inverters and the transformers, all right? Some issues related to the substation and the interconnection to the grid. And finally, the control, monitoring, and communication system that we will need to install. So we will be following more or less this example. We like this drawing from Scatec Solar. It's very, very clear and very helpful in understanding what we will be describing in the next slides. So let's start with the civil works, okay, that we need to think of for the PV field. Joan, you wanted to mention some specific comments about these examples on the foundations. So please, Joan, go ahead. Hello, Joan.
Sorry,
You were muted.
the micro. I was speaking without calling the
problem. That's fine.
Then this is a project in South America of a plant of 30 megawatts.
50 megawatts or 30?
No, 30. 30
megawatts, okay.
30 megawatts. The picture shows the process to driving the principal structural post for PV project. I'm serious driving because in Spanish is hincado. I don't know in Portuguese, but probably, but is the first post you need to drive.
Yeah.
It needs to make previously the geotechnical study and specifically the pull-out test in the site. The pull-out test is important because this is the test evaluate. This test evaluates the capacity of a specific structure to support the restriction by an applied variable force. which means that calculate the capacity of support the force of the wind principally.
Yes.
The process is the same for supporting one-axis tracker or the fixed structures. In this case, is one-axis trackers, but it's the same procedure for our fixed structure. You can the next slides, please, because there are another. This is the same project. Is it at the first structural post I nailed it. In this moment, the second step is the second structural support is waiting on the soil. The procedure to the mountain in this case. It's a little video. As you can pass, it's not a problem. Okay, you can see it's only a bit of the.
You can hear the wind there. The wind is strong.
In this case, HH motor to drag 87 panels. 87 panels that it's composed by 29 panels for 3 strings. It's only is written in the same slide. The panels of the BAD is a panels of Chinese, is important company Chinese. Only not the panels, the electrical vehicles to build this company.
Okay.
And I think there are one more exactly. Is the next steps? The next steps of assembly steps, and the next slide is the micro videos about the run of the motion text. Is the next slide? This.
You can see the trackers. Yeah. Yeah, the testing.
It's a test of a motion. It's a motion text only. Okay.
Mm-hmm. Okay, thank you. So, yeah, after the structural and the civil works, yeah, that are of concern, you can see here the magnitude of these elements. The second aspect that we mentioned is the drainage, yeah. What can happen if in that particular site, if heavy rains, okay, hit the area, like in the example that Johannes has prepared for us, about this 30 megawatt plants in South America, you can see the accumulation of water also in the video before. So appropriate drainage has to be designed, all right? And this is a very important factor that can, depending on the risk of flooding, we might have to discard, okay, to forget about a potential project, okay, if there's too much risk of flooding or the possibilities of building a proper drainage circuit is, complicated or not possible. In any case, the ditches and the access roads sometimes are, built and prepared without taking into account these flooding zones and areas. Roads are prepared to resist floods, but the PV park sometimes will not be able to resist a flood, and we can have serious problems with the foundations, let alone with the electrical system. Okay, so if we have to, incorporate this civil work component in the construction of a PV farm, well, this will impact the works with delays in the planning of the works, additional costs, etc. Okay, if we have to do some kind of refurbishment once the PV park is already up and running, well, it would not affect the electrical production yield of the plant, but it will have some extra cost, right, in terms of repairing or additional interventions. Yes, Joan, you want to add something here in this example?
Yes. it's important that that Paul said it's very important to analyze the flood risk prevention of each power plant. The picture is a real flood, a large flood during the construction of a project. It's not in Argentina in this case, it's in Spain. It's in Spain. It's a power plant that combines PV and thermal solar plant and another district heating and cooling in an industrial area. No, this is really is not it's not a montage. This is
a situation that happened, yeah, in reality.
This has happened. Luckily, it was at the beginning of the wars, and it was necessary to rethin roads and rethin the rain drains for all the plant. It's an important delay of the project.
Okay, so happily, luckily it happened at the beginning, yeah, of the construction work, so there was still time to readapt the planning, yeah. Okay, this is an example on the study, the analysis of the basins, all right, and the projection of what would happen if heavy rains, you know, were to fall on this particular site, yeah. This is part of the site assessment and what can be the civil works to respond to this flooding risk. Yeah, this is a project in Argentina, right, Joan?
Right. It's a project. It's still a project, different investments, but in the same area. And the execution of the solution was cheaper to build as a single photovoltaic PV plant, some of the affected areas of the three projects. The next slide is interesting to see, I think, because this is the solutions what the different interventions of civil works in the construction of the PV plants to minimize of the rise of flooding. The first picture is a protection of elevation and perimeter of prefabricated electric containers is need to elevate, or this exactly. Okay, thank Paul. And the the width of the water discharge is the channels is need to have a good a distance important, no? And the finally, for me, incredible is the need of the underground channels to conduct the water. No? Yeah. You can see in the picture that a main is inside of the channel. No, but this is a good study of the flood risk. No?
So this is, you can see the magnitude. This is the underground, yeah, the channel, yeah, to extract, to be able to convey the water in case of flood, yeah, yes. To drain and drive the water away, right? So that it could get out of the PV farm, yeah. And you can see the size of these channels, so a person can go inside. So it's really a large drainage, evacuation network we need to think of.
The drainage is underground of the PV plants. In the picture, you can see the PV, the panels.
Yes. Okay. You can see the panels. Yes. Mm-hmm. Okay, now let's look at a little bit at the inverters, okay, before we take a break. So for the inverters, we mentioned, for instance, this manufacturer, Sungrow, and their solutions. You can see in the picture here that this come in containerized, all right, solutions already containing the inverter and the transformer, okay, together. And this is just an example from one manufacturer. When we discussed the configurations and the power conditioning session, I already mentioned some other manufacturers from SMA, etc. Different examples. In this case, well, the specifications, again, as we discussed in the power conditioning, very much detailed. The different aspects we have been commenting this morning. This is a model for 30 megawatt PV farm that we have been discussing. On the DC side, we can see this particular model from Sungrow. It can be working with a DC voltage input up to 1,500 volts. Okay, this is one model, and this is another model. This is a 2.5 megawatt model, and this is a 3 megawatt model. So yeah, they have the maximum power point capacity, specifications, voltage ranges of operation. On the output side, they can deliver, as I mentioned, 2.5 to 3 megawatts. Okay, that's the maximum power output.
Paul, it's important the temperature of the reference of power. Huh?
And the reference, the temperature at which this rated power is actually indicated, will give us the maximum temperature these models can work comfortably at. So for higher temperatures than that, not probably the case in Mozambique, but it could be the case in, I don't know, some areas in the Middle East, for instance, or in the desert areas, of California or Chile. Temperatures could be much higher than that. So these models then would not be delivering this capacity. For the voltage range, from 10 to 35 kilovolt per unit, so really flexible. And then that's the inverter. As I said, together with in the same container, apart from the inverter, we will find the transformer, and then the transformer will be able to step up, the voltage, the output voltage of the inverter to the required voltage that we want to send to the substation. Some examples, how installation.
I'm sorry, Paul. This is a project in Argentina. It's the Sungrow inverter. Are mounted inside of an unique container. This configuration do more easy the installation and to make the test run inside, reducing of the time of the walls. It's only pictures to see the procedure of the. It's easy to mount in this container.
Okay, I think very quickly we can mention some issues about the transformers. This is again the same model, from Sungrow, where we can see the transformer. They can adapt the voltage from the inverter to be able to send it to the substation. Any specific comments you want to make here, Joan?
Well, yes, the transformer is integrated, how to say, in the same container. Remember that the slide before, the AC output voltage of the inverters are 0.55 kilovolts. Then this transformer elevates the voltage from this value of this project plan is 33 kilovolts. That is the alternate current voltage of the internal grid of the PV plant. Before the own of substation to evacuation line that is elevated to 132 kilobytes.
Exactly.
A little problem in all the PV plants is the requirement another internal transformer to feed the auxiliary service, has to see before, to reduce or to elevate, it depends, from 0.55 kilobytes to 0.4 or 0.1, I'm sorry, 100, I'm sorry, 0.55 kilowatts is the output of the inverters.
Of the inverters.
And you need 0.4 or 0.20,
220 volts.
220 volts, I'm sorry, is better for me, 220 volts to feed the auxiliary service. And you
Exactly.
need another transformer to auxiliary service.
Exactly. So basically, at the output of the inverters, we would have roughly 500 volts approximately. Then we need the transformers to step that up to the desired input voltage for the substation, 33 kilovolts or a fraction of that. Okay. So more or less, you have a different sequence of stepping up the voltage output. And finally, the substation. We'll have two examples here, right? This is again for the 30 megawatt PV farm, example South America. This is a station receiving 33 kilovolts, receiving 33 kilovolts here and sending 132 kilovolts to the grid operator. So stepping up the voltage and adapting it, frequency, etc., to the requirements of the grid. This was about more or less 2 kilometers, right?
Yes.
To connect.
Yes, it's right. It's right. Oh,
Okay.
2 kilometers of the line between the power plant of the substation of the operator.
Okay, excellent. And another example, of different. This is like in the slide we showed for the floating. Typically you have different parks together.
Yes,
This is the
exactly.
addition of 3 PV parks, 38 or one first plot.
There are a little mistake. Is 28. It's 38.
28, 36. So roughly around.
No, 36. It's only in the first number. Okay.
Yeah. So roughly between 30 and 40 megawatt approximately units of so you can say it's 3 parks or 1 park in a way.
Exactly.
That they were sharing the same substation, I guess, right? So
this needs a new solar. I'm sorry, Paul. This is a new solar substation to elevate from 33 kilowatts to 132. Is a substation of the power plant solar. Because the distance between this PV power plant and the existing substation of the grid operator was of 35 kilometers. Then you need to elevate to the 132 kilowatts to transport an evacuation of energy to the substation of the operator.
Right. So in this case, the distance between the PV farm and the existing substation was 35 kilometers. So different requirements, different situations in the site. And we need to adapt the design of each PV farm to the given conditions of each site and the given situation of the last substation on the grid. Okay. I think now it's a good moment to take a small break, all right, before we continue with the rest of the session. So I propose a 5-minute break. Is that okay, Adelson? What do you think, or Dr. Lucas? Or you prefer 10 minutes?
Can I have a question?
Sure. Yes, Kamal, please.
Thank you for the presentation. Can you let us know, cost-wise, what is the cost of these inverters comparatively to the whole system? If you can say something about it.
What are the costs of the inverters compared to what? Sorry, I didn't get the question, the second part.
You can say absolute values, or you can say comparatively to the system, to the whole system. What is the cost of inverter transformer? Yeah.
Okay, as a percentage of the system. What Joan?
Yes, it depends, but it's between 15 25% of the investment plan, more or less. You can preview that the 40-50% is the panels, the 20% is the grid of the inverters, and others is the rest. More or less, but it depends of the configuration. It depends of the one axis, dual axis, fixed, because it's a total investment about the plan.
Okay, thank you.
So if we were mentioning, Kemal, if we were mentioning a reference of roughly 0.8, $1 per megawatt, sorry, per watt peak, yeah, that would roughly be 800. If that is 0.8, $1 per watt peak, that is $1,000 per kilowatt peak and $1 million per megawatt peak. Okay, that's for the solar field. So you can get more or less a half of that for the inverters. What do I mean? You can get more or less $500,000 per megawatt of inverter power. Yeah, approximately, rough numbers. Okay.
Okay, thanks. Yeah, I was surprised. I was surprised with the efficiency. They're very high efficiency. Yeah, 98%, 99%.
Yes, when they operate close to, I mean, higher than 20% of their rated capacity. Yes, if you operate them at very, very low power capacity, okay, less than 20% of the rated capacity, then the efficiency will be low as well. Yeah. But again, it depends. In this kind of projects, you know, economies of scale are important because you can easily get to very large numbers, and then the unit costs can really change. Yeah, if we are talking about a 10 megawatt project or a 100 megawatt project, yeah, that's a different scale of costs you can find. Yeah. So thanks for the question, Kemal.
I would like also to ask you the possibility for a question.
Yes, please.
Yes, something that always comes into my mind is the areas that we need to use to install the panels. While you are talking about the drainage and while you're talking about the civil constructions, we are talking about quite big areas that if we start from about 30 hectares up to this last example that we are talking about almost 100 hectares. What kind of usage we may do to in between together panels plus what kind of else can we use to take to use, say, the land, because it is almost a land that will do nothing else than the installation of the panels, because actually we also have another constraint is the growing of the population. The land available is always short. What else can we do? In towns is different because you can use roofs, etc.
Yes.
But yeah, I think that you got.
Yes, thank you. Yes, Mr. Frade. Yeah, thank you very much. Yes, I mean, you're right. This is why we started by saying that the conditions of the land, the usage, the ownership, the planning, it's very important, because the requirement for land use is not small. You can use this reference. Obviously, the solar panels are the elements that will require most of the land. So this reference of 1 hectare per megawatt is a good reference. Then you can easily integrate the inverters space requirement as part of this same land reference, because the elements that will require most of the land are going to be the PV panels, whether they come with trackers or not. Yeah. This is a very interesting reflection, the one you are putting on the table. Which one is best to promote in a country? Yes, the solar rooftops. Yeah, installing PV systems in roofs because they are already there, or going for PV farms. Okay. I think the answer probably is somewhere closer to try to consider both, yeah, diversify. Luckily, the photovoltaic technology is very modular, yes. It can be complementary, it can be scaled up and down. So whenever there's possibility to use land that is not needed for other agricultural uses or for human, you know, for the settlement of towns or villages, the PV farms are a good option, yeah, in those areas that are probably not very heavily populated, with this available space, just like any other infrastructure, yeah. If you consider a landfill or you consider a wind farm, etc., you will have the same problematics, yeah. But I agree with you that considering the roofs is also interesting for the photovoltaic future in Mozambique. This is why in this course we have been discussing about the solar rooftop, and in the sessions we will have in January, we will also share with you a session like this today, to talk about examples for rooftops, yeah, because we think it's a very interesting possibility for Mozambique. Okay, so let's take a 5-minute break. Dr. Lucas Adelson, is that okay?
Yeah, I think it's that okay. 5 minutes break.
Okay, thank you very much. So we come back. Okay, let's say 10:30. Okay, this is 7 minutes from now. Okay.
Okay.
We'll come back 10:30. Yeah. Thank you very much. Welcome back to the session. It's time now to continue after this pause. So let's move on. Now, we will mention very briefly some key elements on the communications, monitoring, and control. Because of time, we only have half an hour left now. We will keep some of these slides and some of these contents for when we have a session. We will have a session specifically on operation and maintenance. Okay. This is a session we have scheduled for the beginning of February. So don't worry, we are now going to go through a little bit quick on the presentation of the communication systems, and then we can revisit this, okay, later on. So an important element of our PV farms are the communications and the control, and essentially we have two parts here, what we call the system that will be installed in the same solar plant, okay, in situ, on site, called the solar plant system, the different type of sensors, of different systems controlling the different elements in the PV plant. And then what we call the control rooms, yeah? One control room will be, some elements of the control room will be again on site, and some other elements then could be remote, okay? Remote communications that will be controlled by the project developer or the utility, okay? This will depend on each PV farm and the different setup, yeah? That could be defined. There's a lot of flexibility here, okay? To adapt to different conditions of each project, yeah. Different SCADA elements, different servers, different kind of interfaces with project developer, the utility, the grid operator, the public. Sometimes, if you want to make this some of this data available publicly, etc. Yeah. as I said, I think now we don't want to go into much detail because of time, okay? But essentially we are building databases, different elements that can enable the checking of how the plant is operating, okay? Synchronize this data gathering so that it is accessible for the different institutions or organizations that want to control and supervise the performance of our plant. And eventually we can have one same system that will be controlling different PV farms, okay? That could be together in one same site, like the examples we saw in South America, or it could even be distributed, different sites, okay, across the country. Depending on the business model, if it is a PPA or is it a private project, private developer, or it is a public developer, okay? All these systems can be adapted, and then the kind of information that is produced, statistics, performance indicator, report, alarms, this can be tailor-made, they can be customized, okay, to suit, okay, to adapt to the existing regulations or grid codes or quality assurance protocols, etc. Okay. In any case, the notification of alarms of important aspects of the performance of the plant has to be in place and has to be enabled in the whole communication system. Okay, then different SCADA solutions, different softwares, different approaches are available here. If you remember from the roundtable we had with our colleagues from Ferntech, they were also mentioning the difficulties sometimes on the communications. So the different type of networks, whether it is satellite connection, whether it is standard mobile phone connections, all of that, the availability of such communication networks in the sites that we are assessing is going to be critical. So for that, specific adaptations for each site and each project will be needed. So this communication element in PV farms is critical, and this has to be necessarily well defined in the projects that we want to build. Sometimes where the temptation could be to first, proceed with the construction of the PV farm and then come and retrofit, install on top of that the communication system. Well, I said these systems and these designs are very much flexible, but the cost or the easiness of some of these communications or control systems will be challenged, will be a bit more complicated if we do that as a retrofitting approach rather than part of the initial project, in the beginning, okay? Joan, if you want to add something here and there, just let me know. Otherwise, I'll just proceed to go a bit quickly over this part. And because
no, this is not. The continuous policy. This I think is good. But
yes, we can revisit this later on when we talk about operation and maintenance. Okay. In this slide, we can see what would be the control room in the different parts that are found in the PV farm. Okay, different units. We call the main substation for the solar unit, the MSSU. Then peripheral substations, depending on the layout. Well, to be honest, these are just examples, different configurations. All of this is customized in the end to be able to place the necessary elements to control all the parameters, that we want. Okay, I think that's the key message that we need to keep from this part. And these are some pictures of the main substation unit and peripherals, which they need to be properly communicated, okay? And there are different solutions to that.
Normally, Paul, is the peripheral is normally there are one for inverter, sorry.
Each inverter will have
Each inverter will have a peripheral. More or less, it's not definitive.
Exactly. This is not an absolute approach. You know, with communications, there are different possibilities always. Yeah, very adaptive, and every now and then we have new products in the market that come up, and so it's very much a part of the project that can be customized to serve for the process. And like what we said for monitoring, yeah. It's always, if possible, always better to have a very strong, robust data acquisition system that can enable us a monitoring evaluation, the performance of the plant, and we can then anticipate some preventive maintenance when we can see predictive maintenance as well. We can predict how the plant is operating, and we can anticipate potential deficiencies in some of the equipment, and we can decide whether to fix them, to replace them, etc. Okay. All right. I think we can revisit this part when we talk about on O&M and also the monitoring analysis of plants. Okay. Okay. Some common issues. Sometimes these are problems that have arised in PV farm projects, operational aspects, and also some design aspects, and some aspects that have requested some redesign, okay, of PV plants. We have highlighted 3 aspects. There's many others, but with the time we have today and in this course, we had to make a selection. So we thought of these 3: the grounding issues and potential ruptures or discontinuities of earthing, grounding. Then later on, we will see the interconnection of the strings, of the PV panels for the optimization of the output, formation of the different PV arrays, and finally a couple of reflections on the structural designs. Okay. So the first issue that we wanted to share with you for PV farms are the potential as a problem that could be found in terms of the earthing, the grounding discontinuity. This is perhaps a very technical aspect, not that we want to explain it in detail, but just for you to understand the implications, because the earthing of a PV farm is obviously a complex, construction and civil work, part of the implication of the project. That if it is not planned properly, then having to fix it afterwards is complicated. So this is an example how this earthing or discontinuity was detected. You can see some monitoring graphs here, thanks to the communication systems that we were presenting before, and different inverters, different phases of the output of the inverters. And in this graph here, we could see a difference between one phase and the others, right? The correct situation would be something like this on the right, where the 3 phases are, of course, aligned, okay? And then here we could see some kind of imbalance, in the output of the inverter. This was in a 8 megawatt plant, right, Joan, in Spain?
Yes. This problem was detected in a plant in Spain of 1 megawatts with dual axis tracker, but it was very difficult to find the origin of this desviation. The desviation is more or less on 5% of loss of phase, of 5% of loss of phase respect another. Is small, and then the SCADA system will not generate an alarm. This problem is what detected by an operator of the SCADA, a human person. After 2 months of investigation, 2 months when we need. The problem was resolved that there were a problem of discontinuity of earthing. See, it's incredible, but I can explain before because this is more interesting, this problem.
So the quality of the grounding, is probably not that important versus the continuity. So sometimes the time becomes pressing in the construction work. And the problem is that the civil works sometimes are finished before the electrical testing and commissioning takes place. And then if some defects are detected, then it can be a little bit difficult to reopen trenches, go back to the contractors and the civil works, etc. So this is probably not a huge problem in terms of production, but in this example, in this case, but if the imbalance, if the discontinuity was more serious or affecting larger parts of the PV farm, it could have a serious reduction on the production of the power plant. So these are examples of how a correct earthing installation is done. Some examples, probably those of you involved in power plants or the ones implied, those of you who have had the chance to work in the Makuba works installation, you will know what we are discussing in here. And well, very quickly, the idea how this is happening, if you can give some ideas here, Joan.
Yes, this was the problem. The problem, well, first remember the sentence of Paul. Many times the quality of the earthing is not as important as his continuity. It's more important the continuity of the earthing. No? In addition to the electrical risk that represents to the staff with access of the PV plants, the problems of the earthings, can appear other problems. This is the indicate case about the loss of the 5% of the production between phases. It was a problem relative to the diffuse currents through the structure of the aluminum frame of the panel after the electrical production yields of the plant. The name is the surface polarization or reverse polarity. The electrons, has a fuga, the electrons. Yes. I am sure
there's a leakage
about the structure, the aluminum. Okay.
There's a leakage. There's a leakage of some electrons, of some current. Some electricity was kind of leaking, right, in a way.
Yes.
From the panels, through the structure and to earthing. So in the end, part of the production was being lost through the same structure of the panels, and these are probably small defects in the panels that can be enhanced by environmental factors, humidity, temperature, etc., and little defects that can generate this loss of current.
It's more easy to understand the problem with the next slide, exactly. With this. This is the consequence of the surface polarization or that generate it's puntos calientes, no, sorry.
Hotspots. These are hotspots.
And then I'm sorry.
No, okay.
The picture show that what is the problem, because around of the structure of the aluminum do have a lot of hot spots. It's not normal in I'm sorry, I lost the.
Just a second. Somebody has started sharing. Okay, sorry about that. Coming, just a second. Yes. Is that correct now?
Yes, now. Then to detect this problem is with a thermographic photo. And this is easy because the hot spots is normally there are 1 or 2 for panel, but not 1, 2, 3, 4, 5, 6, 7 for each panel, and near of them the structure of aluminum. No? This is they indicate that the problem is a surface polarization. No?
Yeah.
In this case, was solved the problem not repairing the earthing because it's very difficult to find the general problem, and was injected an inverse current through the DC lines opposite to this polarization. There was energy cost of this intervention represented more or less 0.5% in front of the 5% of the loss of the was occurring. No?
Mm-hmm.
It was solved, but was interesting to find the problem. No? I don't know if another plant is possible, but in this case was evident.
Yeah, no, it is yeah, probably a defect that cannot be detected easily. Yes, as you said, the SCADA system in this plant was not ready to detect this kind of situation. So thanks to the operator, the person that was checking, yeah, the output performance of the inverters, that this unbalance between the phases of some inverters was checked. Yeah. And as you say, it's interesting. Of course, I mean, you can only correct this either by changing the panels or by changing the earthing, which is very costly, very difficult. So the intelligent, the smart way they found in this project was to inject, yeah, this inverse current through the DC lines to prevent this leakage, yeah, that was reaching up to 5%. Yeah. Okay, so reacting in front of some issues. Huh? Okay, another aspect, the strings, yeah, the connection of the PV modules. This leads us to the realization of what happens with PV modules. PV modules are an industrialized product that is manufactured, of course, in large series, in batches. And like any other industrial product, you know, there's a range, a tolerance of qualities, all right? PV modules are a sophisticated product, highly, you know, the production lines are complex, high standards of quality. But there's always, yeah, some tolerances, yeah. This is just an example about what would be the deviations, yeah, in the maximum PowerPoint production capacity of different modules of one same batch. And if we take, for instance, an example, a PV panel that is rated at 405 watt peak, well, the effective wattage of all the panels coming out of that particular line for that particular model, it's between 395 and 415 watt peak. You see, there's a little bit of deviation below and above the standard or the rated capacity of that particular module. So if you buy, if you are planning a small system, well, the effect of this little differences between the generation curves. Remember when we discussed about the working, the operational fashion of the PV panels. Well, the effect of having little differences between PV modules that are going to be connected together by adding let's say deficiencies or the modules that are a little bit below the rated capacity that we expect from one model. If we add tens or hundreds of modules, that can end up translating in some serious reduction of the expected production of a PV farm, because we expect our PV modules to generate 405, and we could be having several modules generating 2%, 1%, 3% below that. So 3% or 2% of many or a large capacity ends up being a substantial reduction on the annual yield. Okay. So in the end, what solutions? Well, this is again more examples of what could be the range of effective performance of a PV panel. This would be the central position, 405 watt peak rated capacity, but this is perfectly accepted by the quality certificates. There's always some tolerance between the reference rated capacity. But in practical terms, what will need to be done is to carefully locate, carefully place the PV panels in our plant so that we connect all the, let's say, low performant PV modules together, so that we build low performant strings and we know very well where they are. Okay, because if we put just one low performant PV panel together with high performant PV panels in the same string, that string then will be affected because of the lower voltage of the lower output capacities of the low performant PV panel. So what we want to make sure is that we group all the low performance or the panels that are performing at the lower threshold of quality together. So this is an example of a large PV pergola in Barcelona. Those of you that have traveled to Barcelona or have seen some aerial pictures of Barcelona, perhaps you have seen this system we call the pergola in the forum in Barcelona, and it is almost half a megawatt peak PV plant. Joan, you want to add something? You want to explain this example here? I think you are muted.
Okay, I speak with a micro. This is well, has to say, this famous project in Barcelona City is in the year of 2004 in the Cultural Universal Forum. It's one of the most spectacular fixed structures in the world. A huge structure made up of 4 layers of different heights, and slopes supports 3,400 square meters of panels, with maximum height of the structure of 54 meters above the sea level. The sea is in near here. Then it's very important to make all the installation at the first time, because it's not possible to correct before. No? Then this is the table of the streets. This is 3 tables with pictures of the construction. The project is 79 strings of 34 panels each to make of the 443 kilowatts peak. And then the plant has three inverters of 125 kilowatts. The impact of the bad peak low power is in some panels was reduced at minimum in this case, because if you pass the next slide, Paul, the last slide of this time, the next, please. The next. What I think you can see the read and the next you can see. I'm sorry. Exactly this.
This is the last one.
Yes, that is one. Yes, and this is there are of three. You can see of the red color is the panels that have low power. This representative, I'm sorry, is a total of 14 panels. 14 about 2,600 panels. It's 0.5%. Only 40 panels. Is a good installation. The manufacturer is correct normally. It's a mistake. Is assumable. Is accepted. It's
an acceptable situation.
It's unacceptable.
Only 14 out of 2,600 panels.
But if these 14 panels can put in anywhere, then at 20 no, the number is 18 of the PV power plant will have been generated at a rate of the 5% less of energy.
Okay.
Each panel is in one string, one panel only, reduce all the string at 5%.
Yes. So if all the, let me revisit this concept. You can see in the graph here, so in this project, what John Antonio and his team, remember this project was in 2004. So we're talking about 16 years ago. So they analyzed, they checked what was the effective power output of each module. You see, each cell here is a module in all this pergola, okay?
Yes.
And if it was green, means that it's above, the rated power capacity. If it's yellow, is within the tolerance limits, and if it's red, is too low. I mean, below the tolerance limits. So all the low performance modules were grouped together in the same series, in the same string. Okay, so that only this string was affected by the low performance, okay, of the panels. If, remember, only 14 panels out of 2,600, so 0.5% of the panels were low performant. But if each of these panels had been placed in a separate string, then 14 strings out of 79 would have been affected and underperforming, you see? And that would have an overall impact of a reduction of 5% less of the energy that the plant is producing at the moment. So by grouping all the low performance panels together, this power reduction is minimized, okay? It's minimized to less than 1%. Okay, so again, this is another issue that, you know, it's part of industrial products, it's part of infrastructure, okay? But if we are conscious about this possibility, then the performance of PV farms can be, you know, can be improved or optimized, okay? Without having to reinstall PV panels and all of that. So these are, again, we thought this was a valuable tip to share with you today. Okay, so the last thing, and with that we will be closing, for today because it's 11 already. Some reflections on the pre-calculated, okay, structural designs. Basically, the idea here is that, okay, some pre-manufactured or pre-designed tracking structures might be, almost universal or very easy to apply to most of the locations. But sometimes the particular location or the particular site we are looking at might have some requirements, some topographic requirements, some climatological, requirements that might need for some specific structure to be designed, or manufactured. Okay, so the bottom line here is that these pre-designed tracking structures are not always suitable for all the locations. Okay. Sometimes the initial investment reduction, as we saw in the example we did for Goodway, is the initial investment can be reduced by using trackers. That is true, without losing, the relative performance or the productivity. We saw the comparison of the fixed versus the single axis tracking, yield in the example of Goodway. But these calculations, this structure have to be, validated, okay, for the real conditions of the site we are thinking of in our plant, okay? And it might seem an obvious thing to say, but again, when time is running and these kind of projects, sometimes the execution times then become a problem, and times need to be shortened up and decisions need to be taken quicker than expected. So these verifications sometimes are not done, okay? Pre-designed structures are, of course, cheaper and are very interesting, but be careful with that, okay? This is the main message that we want to give you, I guess, here. Some pictures for ground experience. Joan, you wanted to share something?
Yes, this is unfortunately the plan of the 30 megawatts in South America. This tracker is a combat tracker. Is a wood tracker. Is not and the manufacturer say that this tracker met all the guidelines and calculation necessary for its assembly in Argentina and anywhere in the world. No? But you can see the problems about the damage produced without wind of 60, 70 kilometers per hour, which is not necessarily the excessively high wind speed higher. Is a high wind, but not is the very high.
Yeah.
Right. The principal conclusions were that the combat is the model of this tracker does not specify the PV model in the calculation of the structure. See, this is the PV model, general PV model, not the exactly PV model, and use the codes, the international codes to calculation, but not the specific code of, in this case, Argentina. In Argentina, there are the CIRSOC. CIRSOC is el Centro de Investigación de los Reglamentos Nacionales de Seguridad para las Obras Civiles. There are a guide that but the use of the action of the wind about the construction. And then another problem, but the load combination used by Combat is the model, are one in some combination. Then the lesson is that is need to recalculate anytime all the structures that you building in your PV farm. Is very important. Recalculate with the codes of the of the country and to know the problems of the wind of another problems in the area. No?
Yeah.
It's real.
Okay.
It's a situation of the it's 1 year only. This problem appears.
Yeah. This problem appeared just 1 year after after finishing the works, and you can see it's a serious thing because you have all the trackers. This is a 30 megawatt plant, right?
That's right.
Already installed and everything connected. The plant is up and running, and then even with winds that were not really strong, because we're not talking about very strong winds, 60, 70 kilometers per hour.
Yeah.
The structure started bending and twisting, and you can see here the PV panels are completely out of position. So this is a real problem, very expensive to fix all of this. So as Joan says, another key lesson from today is that the structures need to be carefully assessed, and as part of our PV farm projects, we need to pay a lot of attention. And with pre-designed or pre-manufactured solutions, let's be very careful that they comply with all the potential situations we can find in our site, or at least the site that we are studying for a PV farm.
It's important. Only one thing: the structure affected is the peripheral structure.
Yes.
Not the middle of the structural. Only the first structure that receives the wind.
Yeah. Yeah, you mean in the PV farm you have like some internal,
The internal was not problem, but the peripheral, the first times of the last is the problem.
Because it was the more exposed, to the wind.
Yes,
so
exactly.
Heating here, and then this was somehow protecting the other ones. Yeah.
Yes.
Okay.
Sorry, can I have a question?
Yes, please.
Yeah, thank you for the presentation. Very nice. Aerodynamics is a very specific science. It's not only about wind speeds. It's about the aerodynamics that you put there. It's a wing, it's an aerofoil.
Yep.
So the effects are completely different than what you expect,
Yes.
So, we see this happening all the time. Advertising, commercial advertisements in big structures fall down also. So it's normal. Yeah, it's a very complex part.
Yes.
Yeah, but my question is about the factory of solar panels in Mozambique, owned by Funai, and what do you have to say about it? Do you ever use those solar panels? Have they been marketed in the projects in Mozambique? If you have any idea, or project that have used the solar panels from Mozambique, so we get some confidence. Yeah.
Okay. I have to admit that I'm not familiar with the PV panels coming out of the factory. I know there were some studies last year or 2 years ago about that factory. Whether that factory could be improved or not, but I'm not familiar with that. I don't know. At least the project I have done, I haven't seen or considered the PV panels coming from that factory. So sorry, I cannot help you with that. Probably we need to speak to Funai for.
Yeah, maybe Mr. Lucas is a local consultant. He can say some
information, but we probably need to Funai to need to go to Funai to investigate that. Okay.
Hello, sir.
Sí, señor Jan, yeah.
Yes, I've sent an email asking for questions. I'm going to design one project for containers. what is specification I have to consider
Okay.
for to launch a tender
Oh.
to contract a company to build it?
Oh, okay. Okay, we will, I have seen your email. We need to discuss, yeah, bilaterally, because
Yes.
preparing specifications is something that requires a bit of work, yeah, and it's not something you can just use specifications from one project that are good for all projects, you know. This has to be
Yes.
discussed in detail, because what kind of project are you thinking of? What is the size? Is it on grid? Is it off grid? What is your project? Off grid.
It's off grid. Yes,
Okay.
it's off grid. What I need the to consider container as a power plant.
Okay.
And I will connect it in off grid.
Oh, okay.
But what is my question? How to ask the company for for supply the
Yeah,
the containers.
I understand.
As a power plant, yes.
What is the size? Is it very big or?
Yes, 75 kilowatt peak
Okay.
and 100 kilowatt peak.
Oh, okay. Okay. Okay.
Mm.
Okay. You see, okay, there are two things here. I think we can probably discuss that, yeah, by email, because it's a very particular question to your project. But the next session
Yes.
we are going to do in January, it's going to be about off-grid, mini-grid design. We're going to do some exercises and case studies, yeah, for design. So
Okay.
in the next session, you will see a lot
Okay.
of design issues. But what you need, you're telling me, is other specifications. So this is the next step, you know. So this is when you really want to buy equipment, and obviously you need a design, but you also need to be, you know, requiring aspects of quality, of certification, etc., etc. Okay.
Yes.
Is
That's
this a project you'll be doing with FUNAI or?
yes. It's belong to FUNAI.
Okay, okay. Because what we can also do is to talk with FUNAI. Sorry, are you working for FUNAI? Are you
Yes.
FUNAI
I'm
official?
working for FUNAI.
Ah,
Yeah,
okay,
I'm a technician
oh, okay, okay. Good,
of
good,
FUNAI.
good,
Yes.
good, good. Okay. Then what we can do is probably put this project as part of the portfolio. Yes, of projects that
Yes.
we will yeah, consider in the next phase of this ERC. Okay, I think Dr. Lucas,
Okay.
are you there, Dr. Lucas? I think Dr. Lucas had some connectivity issues today. I think, yeah, Senor Jaime, the best would be to
Yes.
put your project as part of the portfolio of projects to analyze, because you need more than just an answer to a question. You need assistance, you see,
Yes.
to develop all of that. So
Yes.
what is the name of your project? What is the location, so that I note it down?
It's Mapulangwene, Magude.
Okay. Okay.
Yeah,
Okay.
but I was expect to launch the tender this month, but I think we can discuss particular
You can have a bilateral
about this project
now.
because I have to launch the tender this month.
Yeah. Okay, so we can discuss bilaterally. Okay.
Yeah, what I need it's what I have to consider to to uh, to 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 ask the purchases to give me the fine power plant.
Yes.
Or the
So,
nice the nice one.
I understand, but we need to see the design, how it has been made, before you ask, yeah, you need to launch a tender, and that has different processes, yeah. It's not something
Yes, yes.
can be done in one afternoon. Okay, let's talk
Yes,
about that, yeah, after the session. Okay,
yeah.
so thank you very much. It's now 17 past 11. I think it's time to close the session today. I hope you have learned some aspects on the PV farms. Yes, of course, this is just 2-hour session, and PV farms, we can be talking about PV farms for many more sessions and many more details. Yes.
Okay.
With my colleague Joan Tony, we just wanted to give you like a big overview of the situation of PV farms. And as with the same question from Mr. Jaime from FUNAI, I guess for the next steps of ERC program, when there are project ideas for solar farms, we can be, you know, looking at these projects one by one with the specificities, yeah, and what recommendations we can make for each of the projects. So here you have our contact emails. Myself and my colleague Joan Antoni. Thank you, Joan, for your participation this morning. We can.
Obrigado.
Obrigado. Sí, obrigado. We can revisit some of these questions in January when we talk about O&M again on the communications, and perhaps we can give some more examples on the communication systems and some data from PV farms. Okay. And now this is the last session on the solar component of the course that we are going to do this year. Okay, this is a session PV06 is the last one for this year 2020. So we will this is the last week of the course. Remember, you have one last session on Friday about hydro, and we will be resuming, continuing with the solar sessions. I think it's on the 20th of January, according to the program that we have. Okay, so now we have 5 weeks of break. I hope you can enjoy a good rest and have a good Christmas. And obviously, I wish you all the best for the next year. Okay, 2021. So my best wishes to everybody, and I will see you again. I will talk to you again on the 20th of January on our session on the design of grid mini grids. Okay. So thank you very much. And now we can leave the session. I don't know, Dr. Lucas or Edelson, if you want to add any other things before we close now? No? Okay, so we can close the session now. Thank you, everybody, and have a nice rest of the day, and have a nice break until January. Bye-bye.